Hi students, welcome to Sunil's tutorial. I'm Sunil Bilwani and today we'll be doing this chapter called as thermodynamics. Let's see what do we understand by internal energy. What do we understand by internal energy? The energy which is stored in a substance, which is nothing but a sum of its potential energy and kinetic energy. A substance is made up of atoms. Atoms are going to possess potential energy as well as kinetic energy. The sum of all the energy possessed by a system is called as the internal energy of the system. So what do we understand by internal energy? The energy stored in a substance, the energy stored in a substance which is the sum of kinetic energy of all the atoms on the atoms, molecules, ions of the system, and the potential energy associated with the forces between the particle, right, is called as the internal energy. So the energy stored in the substance which is the sum of the kinetic energy of all the atoms, molecules and ions of the system and the potential energy associated with the forces between the particles. Right? The kinetic energy and potential energy of the nuclei, the kinetic energy and potential energy of nuclei, where else will it be? And electrons. The electrons will also possess certain potential energy and kinetic energy, and the energy associated with the existence or mass of the system. Energy associated with the existence of mass of system is called internal energy. So that is what is my internal energy. So internal energy, in short, internal energy is the total energy possessed by the substance, right? Now, the value of the internal energy cannot be measured, because how will I find out the kinetic energy and potential energy of the atoms, molecules, nuclei, electron and the mass? So I can say that the absolute value of the internal energy cannot be determined, as it is not possible to determine most of the quantities accurately, right? However, when we talk about internal energy, instead of trying to determine the absolute value of internal energy, we try to find out the difference in internal energy, right? I can say that the absolute value of internal energy is U. Okay, the absolute value of internal energy cannot be measured. The absolute value of internal energy cannot be measured, as it is not possible to determine. As it is not possible to determine most of the quantities accurately. Right? However, the change in internal can be determined. Right? You can find out the change in internal energy. However, change in internal energy can be determined. can be determined. Now, energy is transferred into the system on heating or in doing the work, right? And it increases, it is added to the system. Hence, the internal energy of the system would increase when energy is given to the system. Guys, suppose if I take a vessel of water, right, and I heat it, some amount of heat energy is going to be used to heat the water, and the vessel will also get heated. That means some amount of energy is utilized to heat the vessel and some amount of energy is utilized to heat the water. That means when energy is given to the system, besides the external work being done, some amount of energy is given to the system. Hence, the internal energy of the system would increase. Besides external work being done, some amount of energy is given to the system, and hence the internal energy of the system would increase when heat is given to the system. Right? So let's write this down. When energy is transferred into the system by heating or doing work, it is added to the system. Added to the system. Hence, internal energy of the system increases. Of the system increases. Right? So when heat energy is given to the system, the internal energy of the system will increase. On the other hand, when energy is transferred from the system to the surrounding, obviously the energy of the system would decrease, right? And hence the internal energy of the system would also decrease. If energy is given from the system to the surrounding, the energy that is present in the system would decrease, and hence the internal energy would also decrease. So right, when energy is given, when energy is transferred from system into the surrounding, when energy is transferred from the system to the surrounding, either as work or heat, then the internal energy decreases. Then internal energy decreases. So when heat is given to the system, the internal energy would increase. When heat is removed from the system, the internal energy would decrease. Right? Do we get this in here? Okay. Next, now we have already learnt the first law of thermodynamics. The first law of thermodynamics is the same as law of conservation of energy, right? So the first law of thermodynamics states that energy can be converted into work and work can be converted into energy. Now this law was modified, and you had the second law of thermodynamics, which says that there is a spontaneous flow of heat which is always unidirectional from higher temperature to lower temperature. And it was because of the second law of thermodynamics that it was assumed that current flows from the positive terminal to the negative terminal. Remember in physics you all have learnt conventional current. What is conventional current? It is the current that flows from positive to negative. So that is the reason why it was assumed that way. So there is always spontaneous flow of heat in unidirection, and which is always from the higher temperature to the lower temperature. And that is my second law of thermodynamics, right? First law of thermodynamics, according to first law of thermodynamics, process involving flow of heat from the cold end to the hot end is not allowed. It will always be from a higher temperature to a lower temperature. Heat will always flow from higher temperature to lower temperature. That's as simple as that. Fine. So let's write this down. Second law of thermodynamics. Second law of thermodynamics says that the spontaneous flow of heat is always unidirectional. Spontaneous flow of heat is always unidirectional from higher temperature to lower temperature. Temperature to lower temperature. So heat would always flow from higher temperature to lower temperature, right? Now, according to first law of thermodynamics, heat can be converted into work, right? Because when we wrote the first law of thermodynamics, we said that when some form of energy disappears, equivalent amount of some other form of energy appears. So I can say that according to first law of thermodynamics, if I apply first law of thermodynamics, heat can be completely converted into work. Heat can be completely converted into work. Heat can be completely converted into work, but second law of thermodynamics, which is based on human experience, shows that when heat is completely converted into work, there would be either a permanent change in the system or the surrounding, right? But second law of thermodynamics, which is based on human experience, shows that second law of thermodynamics, which is based on human experience, shows that heat cannot be complete. Shows that heat cannot be completely converted into work. Heat cannot be completely converted into work without producing a permanent change. Without producing a permanent change either in the system or the surrounding. That's my second law of thermodynamics, right? Now, if I am considering an isothermal reversible expansion of an ideal gas, work done on the system is exactly equal to the heat absorbed by the system. If it is a reversible process, whatever is the heat supplied to the system should be converted into work for the system according to first law of thermodynamics. If this is true, then the internal energy of the system should be zero, because the total heat that has been supplied to the system is used to perform external work. The total heat given to the vessel is used to only heat the water. If the total heat is used to only heat the water, will the vessel get heated? No. In that case, delta U will be zero. But this is not possible, right? So that is what is your second law of thermodynamics. When heat is given to a system, it cannot be completely converted into work without producing a permanent change either in the system or the surrounding. So the heat given to the vessel cannot be completely utilized to heat the water. Some amount of it will be utilized to heat the vessel also. Right? Do we get this thing here? in isothermal, if I consider an isothermal reversible process, an isothermal reversible process where the temperature is going to remain constant, right? Reversible where the difference between the driving force and the opposing force is infinitely small. So if I consider an isothermal reversible process of an ideal gas, expansion process instead of process, let's take expansion of an ideal gas. If I consider an isothermal reversible expansion of an ideal gas, the work done by the system is exactly equal to heat absorbed by the system work done by the system is exactly equal to the heat absorbed by the system, as we know that the change in internal energy is going to be zero, right? But it causes a change. According to thermodynamics, second law, what did we say? Heat cannot be converted into work unless until there is some permanent change. Now, what is the permanent change? If I am saying that it is an isothermal reversible process, the total work done by the system is equal to the heat absorbed by the system. But yet there will be a permanent change. But it causes a change. And what is the change? The volume. But it causes a change, that is increase in the volume of the gas of the system. Increase in volume of gas of the system. That means total heat energy cannot be converted into total work. Some part of it is going to get either converted, will do some amount of change in either in the system or in the surrounding, right? Now, whenever we apply heat energy to a machinery, some amount of energy that is supplied to the machinery, the entire energy that is supplied to the machinery does not do work for the machinery. Some amount of it is wasted in the form of heat, right? That is also a part of your second law of thermodynamics, that we do not have a machinery which has an efficiency of unity. That means total heat energy supplied is equal to the total work done by the machinery. No, some amount of energy is definitely going to be wasted, right? So you can say that no machine has yet been made with efficiency unity. I do not have a machinery with efficiency unity, right? That means in heat engine, some part of the heat is converted into work and transfers the remaining heat to the sink. I can say therefore in heat engine, if I have a heat engine, some part of the heat is converted to work, some part of heat is converted to work, some part of heat is converted to work and transfers the remaining heat to the sink. Heat to the sink. Now, if some amount of heat is transferred to the sink, that means definitely the efficiency is lost, right? If some amount of heat energy is not utilized to perform work, that means the efficiency of the machine therefore cannot be unity, right? So I can say thus it has an efficiency of less than unity. Thus, it has an efficiency of less than unity. It has an efficiency of less than unity as efficiency of machine is given by the formula. Efficiency of machine is the ratio of work done, ratio of work done to heat absorbed. The total heat that is absorbed by the machinery is not used to perform work. Some of it is going into the sink, and that is the reason why the efficiency of the machine cannot be equal to unity. So that was my second law of thermodynamics, right? Next, I have also explained to you what is enthalpy, right? Now let's see what are the different types of enthalpy. You can have enthalpy of phase transition. Now, enthalpy is nothing but it is the amount of heat energy absorbed or evolved at constant pressure. Now, what do you understand by enthalpy of phase transition? Is when the amount of heat energy absorbed or evolved at constant pressure when a substance is getting converted from one phase to another phase. That means if I am converting ice to water at constant pressure, then the amount of heat energy that would be absorbed or evolved would be called as enthalpy of phase transition. So in short, it is the amount of heat energy that would be absorbed or evolved at constant pressure when a substance gets converted from one state to another state. Instead of using the word state, I will be using the word phase. Okay. So what is enthalpy of phase transition? Enthalpy of phase transition is the enthalpy change during the transition of one phase of a substance into another. That would be your enthalpy change, enthalpy of phase transition, right? It is represented as delta fusion H. Fine, do we get this in here? So this is going to be my enthalpy of phase transition. Then I can have enthalpy of phase transition. Leave it as it is. Next, what is enthalpy of fusion? Right? Now when we talk about enthalpy of phase transition, you can have three different types of enthalpy of phase transition. You can have enthalpy of fusion, vaporization and sublimation. Right? What is enthalpy of phase transition? The amount of heat energy that would be absorbed or evolved when a substance gets converted from one state to another state. Now this is further divided into three different types. One is called as enthalpy of fusion. What is enthalpy of fusion? It is the change that accompanies the fusion of 1 mole of solid without a change in temperature at constant pressure. So when you are changing a substance, 1 mole of a substance at constant pressure, the change that would occur in the heat energy would be called as enthalpy. Right? For example, Suppose if I convert ice to water, then the amount of heat energy that would be absorbed by it would be enthalpy of fusion. Fine, do we get this in clear? Suppose if I had water solid, that's your ice, and I convert it into water liquid, right? In that case, the amount of heat energy that would be absorbed during this change would be called as enthalpy of fusion, right? Say suppose let's assume that this is say 6.01 kilojoules per mole, right, at 0 degrees Celsius. So that would be called as my enthalpy of fusion. What does this equation indicate? It indicates that melting of 1 mole of ice at 0 degrees and 1 atmospheric pressure would require 6.01 kilojoules of energy. So the amount of heat energy that has to be given to convert a substance from solid state to liquid state would be called as enthalpy of fusion. In simple language, the amount of heat energy that would be required to convert a substance from solid state to liquid state at constant pressure would be called as enthalpy of fusion. Do you understand this? So can we write this down, guys? What is enthalpy of fusion? It is the enthalpy change that accompanies the fusion. What do you understand by fusion? Change from solid state to liquid state. That accompanies the fusion of 1 mole of a solid. So the amount of heat energy that I need to give to 1 mole of solid to convert it into liquid would be called as your enthalpy of fusion. I am trying to give you the same definition in different words so that you understand this. So enthalpy change that accompanies the fusion of 1 mole of solid without the change in temperature, at constant pressure is called enthalpy of fusion. Right? Do you understand this? Right? So do we understand what is enthalpy of fusion? From the equation, I hope you understand that what does the equation say? It says that 1 mole of ice would require 6.01 kilojoules of heat energy to convert it into 1 mole of water. Fine, do you get this in here? Next, what do you understand by enthalpy of vaporization? Enthalpy of vaporization. Suppose if I have 1 mole of water at constant temperature and pressure, then how much heat should I give it so that I get 1 mole of gas? That would be my enthalpy of vaporization. It is nothing but the enthalpy change that accompanies vaporization of 1 mole of liquid at constant pressure and changing temperature. Right? So suppose I could give you the equation this way: water gets converted into steam, right? Then the amount of heat energy would be my vaporization. Enthalpy change of vaporization would be, say, at 40.7 kilojoules per mole at 100 degrees Celsius. That is the amount of heat that has to be given to 1 mole of water to get 1 mole, right? That is the amount of heat that has to be given to 1 mole of water to get 1 mole of gas at that constant temperature of 100 degrees Celsius. Suppose if I had 1 mole of water at 100 degrees Celsius, how much more heat should I give it so that I get 1 mole of gas at that same temperature would be my enthalpy of vaporization, right? So can you just write this down? Enthalpy change that accompanies vaporization of 1 mole of liquid change of 1 mole of liquid without changing its temperature at constant pressure is called enthalpy of vaporization. Right? So that's my enthalpy of vaporization. Next, enthalpy of sublimation. Now by now it should be very clear to you what is enthalpy of sublimation. The amount of heat that I would require to give to 1 mole of a substance at constant temperature and pressure to convert it from solid state to gaseous state, right? So suppose if I had the amount of heat that would be required to convert from solid to gas. Suppose if I have water solid, how much heat should I give to it so that I get water gas? That would be my enthalpy of sublimation. Fine, do we get this thing here? So suppose if I say that delta sub heat is say 51.08 kilojoules per mole at 0 degrees Celsius, then that means 51.08 kilojoules of energy has to be given to it, has to be given to 1 mole of solid, has to be given to 1 mole of ice, so that I get 1 mole of gas at 0 degrees Celsius. Fine, do we get this thing here? So the enthalpy change that accompanies the conversion of 1 mole of one mole of solid directly into its vapor at constant temperature and pressure is called enthalpy of vaporization. Right, so that is going to be my enthalpy of vaporization. So these three are enthalpy of phase transition. So if they ask you what are the different types of enthalpy of phase transition, there are 3 different types of enthalpy of phase transition. You can have enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation. Fine, do we get this in here? Next, let's see what are the enthalpy of atomic or molecular changes. So, when we talk about enthalpy of atomic or molecular changes, you can have enthalpy of ionization. Enthalpy of ionization. Right? Now, what do I understand by enthalpy of ionization? The enthalpy change that accompanies the removal of electron from an atom or an ion in 1 mole of gaseous state is enthalpy of ionization. Suppose let's assume I have sodium atom in gaseous state. Let us assume, guys, if I have sodium atom in gaseous state, how much heat energy should I give to this sodium atom so that I get sodium ion? Is called as enthalpy of ionization. I need sodium ion in gaseous state and I want to remove 1 electron. Right? So the amount of heat energy that should be given to a substance so that I convert it from atomic state to gaseous state, atomic state to ionic state. Right? For example, suppose if I say that ionization is say 494 kilojoules per mole. That means if I have 1 mole of sodium in gaseous state, I need to give it 494 kilojoules of energy so that I get 1 mole of sodium in ionic state. That is the amount of heat energy that is required to remove 1 electron from sodium. Fine, do we get this thing clear? Let me just write this down. The enthalpy change that accompanies the removal of an electron from each atom or ion in 1 mole of gaseous atoms or ion. The important thing to note here is that the reactant has to be in gaseous state. So in 1 mole of gaseous atoms or ions is called enthalpy of ionization. Right, do we get this thing here? So that's my enthalpy of ionization. So enthalpy change that is required for removal of an electron from 1 mole of a gaseous atom would be called as enthalpy of ionization. Now suppose if I am removing the first electron, then that is called as first ionization enthalpy. If I am removing the second electron, then it is called as second ionization enthalpy. Right? Now between the first ionization enthalpy and the second ionization enthalpy, the second ionization enthalpy will be greater than the first. Why? Because it is going to become more difficult to remove the second electron from an atom than the first electron. Reason? Because when you are removing the first electron, the atom is electrically neutral. So you require a certain amount of energy. When you are removing the second electron, it is not an atom, it is an ion which is positively charged. Since it is positively charged, it will have a strong affinity or strong force of attraction for all the electrons. Hence, a greater amount of energy will be required to remove the second electron. Fine, do we get this thing here? So you would get this as your CET question or MCQ question, that the enthalpy, the second ionization enthalpy and first ionization enthalpy, the relationship between them, the second ionization enthalpy is greater than the first ionization enthalpy. Right? I'll just write this down. Enthalpy change for removal of 1 electron from 1 mole of gaseous atom is first ionization enthalpy, and that for the removal of second, and that for removal second electron from 1 mole of gaseous atom is second ionization enthalpy. So you will have first ionization enthalpy and second ionization enthalpy. I can say that the second ionization enthalpy is greater than the first. Greater than first.
So
The second ionization.
this removal of second electron will be from 1 mole of gaseous atom.
It will be from 1 mole of gaseous ion, right? So, from 1 mole of gaseous ion, right? So, the second ionization enthalpy is greater than the first, as it is difficult. To remove an electron. Remove an electron from positive ion, as it is difficult to remove an electron from positive ion due to the strong attraction between the electrons and the positive ion. Between electrons and positive ions. Right? Now, the reverse process would be gain of electrons. So the electron gain enthalpy is the enthalpy change when 1 mole of a gaseous atom of an element accepts the electron. So instead of asking you enthalpy of ionization, if they say enthalpy, if they say electron gain enthalpy, what would be electron gain enthalpy? It would be the amount of energy that would be absorbed or given out when ion absorbs an electron. Fine, do we get this thing here? Okay, let's move on to the next one. Suppose if you have enthalpy of atomization. Right? It is nothing but it is the enthalpy change that accompanies dissociation of the molecule in 1 mole of gaseous substance into its constituent atoms. Suppose let's assume that I have methane gas. Right? I give it some amount of heat energy such that it gets converted into carbon gas and hydrogen gas. Right? How much heat energy would be required to convert methane into its constituent atoms would be called as enthalpy of atomization. Finally, get this in clear. Suppose if I would say that enthalpy of atomization is say 1660 kilojoules per mole, right? That means 1660 kilojoules of heat energy has to be given to methane so that I get carbon and hydrogen gas. That would be called as enthalpy of atomization. We just write this down. Enthalpy change that accompanies the dissociation of all the molecules in 1 mole of a substance, gaseous substance into gaseous atoms is called enthalpy of atomization, right? That's my enthalpy of atomization. Next, you can have enthalpy of, say, solution. Now, enthalpy of solution is it's defined as the enthalpy change in a process when 1 mole of a solute is dissolved in specific quantity of solvent to form a solution. Suppose if I take 1 mole of sugar and I dissolve it in water, or if I take say 1 mole of NaCl and I dissolve it in water, then the amount of heat energy that would be absorbed or evolved would be called as enthalpy of solution. The amount of heat energy absorbed or evolved when 1 mole of solute is converted into solution by dissolving it in a definite volume of water. Fine, do you get this thing here? Do we understand this? So what do we understand that by enthalpy of solution? It is nothing but the is defined as the enthalpy change in the process when 1 mole of solute dissolved one mole of solute is dissolved in a specified quantity of solvent so as to form a solution. Solution of particular concentration. Right, at given temperature. That would be my enthalpy of solution. For example, if I take 1 mole of sodium chloride and dissolve it in water to form 1 mole of sodium chloride solution. Example, 1 mole of NaCl is dissolved in water to form 1 molarity of sodium and chloride. This is the concentration of sodium chloride that is formed, 1 molar of sodium chloride solution. Right? Then 4 kilojoules of heat energy is absorbed. And then 4 kilojoules of heat is absorbed. If 4 kilojoules of heat energy is absorbed, then this 4 kilojoules of heat energy is nothing but my enthalpy of solution. I can say therefore enthalpy of solution of NaCl is plus 4 kilojoules per mole. That is my enthalpy of solution. Fine, do we get this in clear? Now, the exact value of enthalpy for solution is given for a given substance is the sum of the contribution of 3 kinds of interaction. Why do I have this enthalpy of solution? Because of 3 different types of interaction. When I have 1 mole of solute and I'm going to put solvent in it, there are 3 different types of forces or 3 different types of interactions that will take place there. One is the solute-solute interaction, then I have the solvent-solvent interaction and the solute solvent interaction, right? It is because of these three interactions that you have enthalpy of solution. Right, we get this in here. I can say that the exact value of enthalpy of solution for a given substance is the sum of the contribution of three kinds of interaction right. One is the solute interaction, the second is the solvent interaction, and the third is the solute solvent interaction. It is because of these three interactions that you have enthalpy of a solution. Question: what do I understand by solute interaction? Right? For a solute to dissolve, energy is required to overcome the force between the adjoining solute molecule. If I want solute to dissolve in a solvent, then that solute, some energy is required to overcome the forces between the solute particle. Those forces will form the solute interaction. Fine, do we understand this? What do I understand by solute interaction? Solute interaction. When you talk about solute interaction, for solute to dissolve, the energy is required to overcome the forces between the particles, right? That is called as solute interaction. Fine, do we get this in here? Then I could have solvent interaction. The dissolution process, energy is required to separate the solvent molecules from each other to make space for the solute molecule. If I am going to have dissolution, the solvent molecules are closely packed. Now some space has to be made so that a solute molecule can fit somewhere in between them. So that energy that is required to separate the solvent molecules so that a solute molecule can fit into them is called as solvent interaction. So what is solvent interaction? Solvent interaction, right? Solvent interaction in dissolution process energy is required to separate solvent molecules from each other. I require some amount of energy to separate the solvent molecules from each other to make space for solute molecules. I need some space wherein I could fit the solute molecules by overcoming the attractive forces attractive forces among solvent molecules. That's my solvent-solvent interaction. And the final is solute-solvent interaction. What do I understand by solute-solvent interaction? The interaction between the solute molecules with solvent molecules is called as solvation, right? So that is your solute-solvent interaction. I had solute molecules, I had solvent molecules. Now the solute molecules are going to form a force of attraction with solvent molecules. That is going to be my solute-solvent interaction, so that I get a homogeneous solution. Right? Do we get this in here? I can say that the interaction of solvent molecules with solute, the interaction of solvent molecules with solute particles is called solvation. Right? Now, so for solvent water, it is a hydration process and energy is liberated, and that energy would in that case be called as enthalpy of hydration. So you would have some solute that has to interact with the solvent so that a solution is formed, and that will be called as your solute-solvent interaction. Right? We'll see about these interacting forces again in detail in the next lecture. We'll stop this here for the day. Thank you very much.